All right, so our first step today is to figure out how many sig figs or significant figures are in a certain measurement that we're given. There are 5 rules to follow, and they're pretty easy, especially the first 3. So remember, significant figures are there to show us how precise or how good our measuring device is. And that's where these come into play. The last significant figure that's written could be plus or minus 1 from there. So we look at our sig fig rules, which you have in your notebook. Step 1 is to look for all numbers that are not 0, and those are automatically significant. So my 1 here, that's not 0, and the 8, that's also not 0. It's definitely significant. Rule number 2, if I have any zeros before that first non-zero, so my first non-zero is 1, I don't have any zeros before it, so I can ignore rule 2. But we call those zeros leading zeros if there were. If there were zeros over here, those are leading zeros. They are never significant no matter where they're at, as long as they're before the first non-zero digit. Rule number 3, a 0 trapped between 2 non-zero numbers. So these 2 zeros right here are trapped between 1 and 8. And those are significant. They're not just placeholders. They're there to show that we were able to measure all the way down through there. And rule number 4 for this one, any 0 at the end of a number, also called a trailing 0, is significant if it's after a decimal place, because that shows us that our measuring device was able to measure not just to here, but we know that's 0 and we know that's 0 all the way down to here. So for this question, we know that there are 1, 2, 3, 4, 5, 6 total sig figs. For the second one, again, when you do this, it might get a little bit confusing going through the rules, but just make sure that you've checked every number here. Every number should be highlighted. You don't have to highlight them in real life, but on here I'm going to highlight them to illustrate it. But make sure that you've checked each number to see, or each digit to see whether it's significant or not. So 7 and 8 and 9, 7, 8, 9, that's why 6 is afraid of 7. Those are significant because they're not 0, so they are significant. And then we don't have any zeros before the 7. We don't have any trapped zeros. We don't have any numbers or zeros at the end after a decimal point. So we're on to rule number 5, a 0 at the end of a whole number, which is also called a trailing 0. But if it's a 0 that's a part of a whole number and it's before a decimal point, we assume that they are not significant. We're not really sure. That's where scientific notation comes into play. But we cannot assume too much about our measurement. We have to just take our best guess and assume that those are not significant. So this would be just 3, 1, 2, 3. Now remember, we go from when we look at a measurement, we can assume that it's plus or minus 1 in the last significant digit. So this one could be 1.00799, or it could be 1.00801, or it could be this number. So I'm saying I know all of these numbers up to here, and then it's within this range. For this guy, since this is our last significant digit that we know for sure, this could be anywhere between 7,900,000, because plus or minus 1 from here, that would bring that up to 90, or 7,880,000. So anywhere within this range would be an acceptable number. Now, perhaps our measuring device measured all the way to the, I don't know, let's say hundredths place. I know for certain that this one's 0, and I know for certain that one's 0. If I'm just looking at this whole number as it's written here, I can't assume that. But there's really no way for the scientist to report this answer and tell me that this is significant. The only way to do that is to write it into scientific notation, which we'll do some practice on. But basically, in scientific notation, that number normally, when you do that, looks like this. This tells us, anytime you see scientific notation, any digit that's written before the times 10 to the part, any digit here would be significant. So right now, I've got 1, 2, 3. According to my instrument, I was able to measure down to here, so we're going to call that significant too. So 1, 2, 3, 4, 5. So I need to add these 2 zeros here to show that there are 1, 2, 3, 4, 5 significant figures. This is the only way, with scientific notation, this is the only way to show whether this 0 is significant or not. I'm going to say it one more time just to make sure you get it. If you're given a whole number like this, you cannot assume that this is significant. You have to assume that it's not. You have to assume that the measuring device was so imprecise that it was all the way over here to the 10,000ths place where we had a degree of uncertainty. The only way to show that we were able to measure all the way to the hundreds place here is to put it in scientific notation and show that those zeros are a part of it. If we didn't include this 0 right here, that would mean that maybe we measured to the thousandths place instead of the hundreds place. If we added another 0, that'd mean we measured to the tenths place. And then whichever last significant figure that happened to be is plus or minus 1 from there is the range of uncertainty that we have. All right, let's do another one. Let's see. Rule number 1, all numbers that are not 0 are significant. So that's not 0, that's not 0, that's not 0. Any zeros before the first non-zero, so any leading zeros, are just placeholders, and they're not significant. So 5 is our first significant figure here. Anything before that, any leading 0, is not significant. So nope, 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 nope. And now we've accounted for all of our digits in the number. We're going to say that this one has 1, 2, 3 sig figs. And the last one. We know that is significant, 3, 4, and 5. Rule number 2, any zeros before the first not 0. So these guys here, our leading zeros, are not significant. Rule number 3, any zeros that are trapped. So this guy's trapped, these two are trapped. Those are significant. And rule number 4, any 0 at the end of a number, so any trailing 0, if they're after a decimal, so our decimal points here, these are trailing zeros to the right of a decimal, they must be significant because we're saying our measuring device goes all the way down to that point. So I'm going to call that 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits or significant figures. Now, when we calculate, if we have to do any math, adding measurements together or multiplying measurements, especially when we do unit conversions, it's not fair to us to report our final answer to a level of less uncertainty than what any of our least uncertain measurement was. So if I had a not very precise measurement, or not very, it didn't go down to a multiple decimal places or something, it's not fair for me to report an answer that's more precise or less uncertain than that. So there's two different rules we have. If we add or subtract, we're focused on how many decimal places there are. So we want to find which of our numbers have the least amount of decimal places. This one has 2 decimal places. This guy only has 1. This guy's got 3. So we're going to do to round here. Whatever we get when we punch this in the calculator, 10.03, which happens to be 29.464. I'm saying that I want to round to the tenths place because this one is the smallest decimal here, or it's the one with the least amount of decimal places. So I'm going to cut this off after the tenths place. And that 6, it's bigger than 5, or it's 5 or bigger, so it rounds up. And so now we're going to get that our answer is 29.5 centimeters. And that should make sense, because if I read this number in science, I'm saying, if I reported this correctly, I am somewhere between 29.4 centimeters and 29.6. So I'm somewhere between 29.4 and 29.6 centimeters, which 29.464 obviously is. Let's do another example with adding. This also works for subtracting. It's the same rule. I have 0 decimal places on this first one. I also have 0 here, and I've got 2 here. So I'm going to round to the nearest whole number. I don't want any decimals because I didn't have any decimals in any of these measurements here, or in these two anyway. So 54 plus 1.12 plus 20 is probably about 75.12. Now, like I said, I don't want any decimals, so I'm going to round right there. The 1 would round down, so my actual answer is 75.1 inches. Okay, the next one, we're going to multiply, which has a different set of rules. Instead of looking at decimal places for multiplication or division, we are looking at the least amount of significant figures. So first, we need to go through and count our sig figs. This one, let's see, we've got the 1 and the 3, obviously, and then our 2 zeros are trapped, so this one has 4 sig figs. These are both not zeros, so we have 2 there, and all of these are not zeros, so we have 5. So this one, again, is the one that we're going to use for our rounding. So when I punch that into the calculator, I get 920.808162 centimeters cubed. Now that's a lot of decimal places. If I were to just leave it like this, I would be communicating to the rest of the scientific community that whatever measurements I did, maybe this was a rectangular prism and I measured with 3 different types of rulers that have different levels of measurement on there, and I was trying to find the volume, and I did all of this. When I write that many decimal places, I'm reporting to the scientific community that I was able to measure to that many decimal places. And I simply can't. The best measurement I was able to do was just to 1 decimal place. So it's trickier with multiplication and division because it gives us a lot of weird numbers. Addition is pretty fair as far as decimal places rounding. It makes sense that we would round to decimal places for addition or subtraction. But for multiplication, the numbers get funky and the units change, and it's a whole thing. So we round to the least amount of sig figs, which happens to be 2 in this case. So we're going to count over from the left, 1, 2 sig figs. We're going to cut it off there. That 0 doesn't change anything, so we're just going to call it 920. Remember, trailing zeros at the end of a whole number are not significant, so we still have 1, 2 significant figures, and that would be correct. If for some reason, let's say this was 8.10 instead, we would have 1, 2, 3 significant figures because trailing zeros after a decimal are significant. So instead of rounding there, we would have rounded here. We'd call it 1, 2, 3 digits over, and we round it. This would end up being 921 centimeters cubed. So let's do the next one. 54 times 1.12 times 20. That gets us an answer of 1,209.6 inches cubed. Remember, we're looking for sig figs on this one. So here we have 54, that's 2 sig figs. 1.12, that's 3 sig figs. 20, remember, trailing zeros at the end of a whole number are not significant, so that is just 1 sig fig. That means we're going to cut this off after 1 digit from the left. And we're going to round from there. So we could call this 1,000 inches cubed. I know it doesn't make a lot of sense because you're like, oh, 1,000, this was 1,200. That's crazy. That's way off. But remember, when we look at the number 1,000, we're saying that could be anywhere between 0 to 2,000. It's plus or minus 1 from the last significant figure. Maybe this was 20 with a decimal point after it. Remember, if we slap a decimal at the end of a whole number, that is to signify that that 0 is also significant. So maybe this was 2 sig figs, and we would round here. That would just round to 1,200, which is a little bit more precise, or more, it gives us better data than just 1,000, and that means that we would be somewhere between 1,100 to 1,300, which gives us a lot smaller of a degree of uncertainty, right? We got a much smaller range to look at here. To do scientific notation, you've done this before, like since 7th grade, so it shouldn't be that difficult. But basically, you find where the decimal is. Our decimal would be here. And you bunny hop it over 1, 2, 3, 4 spaces on this one until you get just one not 0 number to the left of the decimal. So this would be 2.95. And then, after you do that, it's times 10 to the, we know it's 4. Is it positive or negative 4? Here's the trick. Positive exponents on the 10 means it's a really big number, or it's a number bigger than 1. Negatives mean it's a decimal, number smaller than 1. So if we have a positive exponent, that means The number is bigger than 1, so we're going to leave this positive. 2.95 times 10 to the positive 4 is what we'd call that. For this guy, we move him 1, 2, 3, 4, 5, 6, 7, 8 places over. So 6.5 times 10 to the 8. Easy peasy. Now, remember, if we're counting sig figs, we'll throw that back in here for a second. You have to assume that all of these zeros here are not significant, because there's no way to indicate that they are. It's very unlikely that somebody measured something and was only able to measure it to the 10 millionths place. They probably measured all the way maybe down to here, but there's no way to report it if you're going to write it like a whole number like that. The only way to do that is to report it as 6.50000 times 10 to the 8. And that tells us that we had 1, 2, 3, 4, 5, 6 significant figures there that we were able to measure all the way to this place. And the rest of those are not significant. That's why scientific notation is important. It's not just to get rid of the big or really small numbers. It's to show for sure how many sig figs there are. Remember, to count sig figs with scientific notation, you just count how many digits there are. You don't have to worry about any rules. Anything before the times 10 to the part is significant. All right, this one we got to move in the other direction. 1, 2, 3, 4, 5 places. So 8.2 times 10 to the negative 5. Negative because it's a number smaller than 1. This one we move 1, 2. So 1 point, well, we know it'd be 1 times 10 to the negative 2. A question you might have is, what do we do with these two zeros? Since we know our sig fig rules say that the 1 is significant and trailing zeros after a decimal are significant, we have to include those in the scientific notation. So we'll call it 1.00, and that tells us that we've got 3 sig figs. So 1.00 times 10 to the negative 2. We didn't do that over here, and we can't do that over there because there's not a 0 here. If we were to put a 0 here, we'd be lying and saying that we were able to measure all the way down to that place, and we weren't. The backwards, to get from scientific notation to a regular number, just write out the number. Remember, if it's a negative exponent, that means our written out number is less than 1, so we're going to move it this way, 1, 2, 3, 4, 5 places, and then fill in your holes with zeros. So 0.0000186. We got 4.53 times 10 to the 5. Remember, we move that. If it's big, or if it's positive, that means it's a big number, bigger than 1. So we move it to the right. 1, 2, 3, 4, 5. Fill in our holes. We would not put a decimal at the end of this because we didn't have zeros here to show that those are significant. So we're going to say these are not significant because they're trailing zeros at the end of a whole number. They're not significant. It's just the 4, 5, and 3 there. 1 times 10 to the 7, that'd be 1 with 7 zeros after it. Easy peasy lemon squeezy. And 6.1 times 10 to the negative 3. We take our 6.1, move it over 1, 2, 3 places. Negative means to the left. So it's 0.0061. All right. So next, we have unit conversions. Here are your steps to dimensional analysis, and over here is our unit conversions reference sheet. We're going to get used to how to use this. First step is to write down your beginning measurement, so 54 inches. Step 2 is write a big X and a fraction bar. Step 3 is to fill in your fancy form of 1. Remember, a fancy form of 1 is just a conversion factor. So for instance, I know, and this is easy, this is the same example I did in the notes, I think, inches and feet. There are 12 inches equals 1 foot. We have that over here, 12 inches equals 1 foot. Any conversion factors you need for this class will be over here. Do not go Google and find other conversion factors. You are welcome to Google the conversion itself, find the answer, and check your answer, but I am going to grade you on all of the work for the dimensional analysis that we do to set up our problem. I honestly do not care whether you can convert units or not. I do care whether or not you can do dimensional analysis, because it'll come up later when we hit stoichiometry in like unit 5 or 6 in the spring. So 12 inches over 1 foot. If I were to divide each side by 1 foot, what happens to the 1 foot over 1 foot? Well, it cancels out, and we're left with 1. So I'm saying that 12 inches over 1 foot is equal to 1. I could have done it the other way and said that, or divided by 12 inches, and I would have gotten 1 foot over 12 inches. And that is also equal to 1. So that's where I get the phrase fancy form of 1. It's just a fancy way to say 1. So the next question we got to fill that into our fraction bar here. That's why we wrote the fraction, so that we can fill in our conversion factor. Anytime you see something equals something, you see this many bases equal omega, or this many teaspoons equals a tablespoon, you can slap that stuff, the number and the unit, on a fraction bar. Either way you need to do it, doesn't matter. What I do know is that I have inches here, so I need inches on bottom on the next step. That way inches cancels out, because under the fraction bar means divide. And above the fraction bar, or just by itself, means times. So inches divided by inches cancels that unit out. So of my two conversion factors, 12 inches over 1 foot or 1 foot over 12 inch, I'm going to put the 1 foot over 12 inches into my little fraction bar. Now if you punch that in the calculator, you do 54 times 1 divided by 12. You can skip the 1 even, because 1s don't change the number. 54 divided by 12 gives us 4.5 feet. It just so happens 54 is 2 sig figs, and so is 4.5, so we don't even have to do any rounding for this one. That was a US to US conversion, and those conversions are found here on the middle of the chart. Anytime you're going from like feet to inches, or ounces to pounds, or tons to pounds, or any kind of volume that has, quarts or pints or fluid ounces or cups or anything like that, those are US to US conversions. This one is an SI, or a metric to metric conversion, and all of that can be found here. For our class, anytime you see the word base, that can be replaced with one of these 3 base units, the meter, the liter, or the gram. And it shows an example here of how that works. So we have the prefix. We would just add giga to the base, so meter, or mega, meter, kilo, meter. And for the abbreviation part of it, which you see more often than the written out word, you just add the abbreviation letter that's here to whatever abbreviation our unit is. So gigameter is a big capital G with a little m, or millimeter is a little m next to a little m, or centimeter, which has the abbreviation C, is a C with the m for meter. Those all work the same way. It doesn't matter whether it's meters, liters, or gram. All of this is exactly the same. So first step for the dimensional analysis of the conversion, we do 56 grams. Start out with what we know. Times, do a fraction. I want grams to be on bottom because it's on top here. So we're going to put grams here. And grams is our base unit, so look for bases. And I want to get to milli. So right here, 1,000 milli is 1 base. So 1,000 milligrams is 1 gram. So I'll write that in. 1,000 milligrams equals 1 gram. So 56 times 1,000 equals 56,000 milligrams. And that's my answer. Next, we have centimeters or feet to centimeters, so we'll start with 3 feet. That is, feet is a US unit, and centimeters is metric. So we're going to need one of these conversions down here. Doesn't matter which one you use. It's length, so you got to pick from one of these two. But either way, you'll get to pretty close to the same answer. We'll do it both ways to show you that. So let's do the probably more obvious one first. We'll do 3 feet. We want to use the inches to centimeters. Can't do anything with inches yet, or centimeters, because I'm in feet. But I do know that there's 1 foot for every 12 inches. So 1 foot on bottom, so the feet cancel out, over 12 inches on top. Now this one's a 2-stepper, so we're going to do another times and another fraction bar. According to the US to SI conversion, 1 inch, we'll put that on bottom since it's on top on the previous step, is 2.54 centimeters. So now we'll punch it in our calculator. We'll do 3 times 12 times 2.54, and we get 91.44 centimeters. Now remember, we want to round to the right number of sig figs. We're going to pretend that this said 3.0, so that makes things a little bit easier for us. I mean, it's easy either way. If it were just 3, we'd cut it off here and round it to 90. But let's say it was 3.0. I'll even fix that over here. And now I know I've got 2 sig figs, so I'm going to go 2 digits over, cut it off right there. So as that 4 doesn't round up, it just stays there. So I'm going to call this 91 centimeters. And that says I could be anywhere between 90 and 92 centimeters. Anything in between that would be fair game. I could have done it a slightly different way and picked the yards to meters conversion. But again, I have to get to yards first. So I know that there are 3 feet and 1 yard. So we'll do 3 feet on bottom. There's 1 yard on top. And then for every 1 yard, we had 0.91 meters. So I'm in meters. Oh, here's the trick. Look over here. Meters is my base. I want to get to centi. So 100 centi and 1 base. 100 centimeters and 1 meter. So that is 1 meter is 100 centimeters. And that's how I get 91, because 3 divided by 3 is 1, then 0.91 times 100 is 91 centimeters. Either way, I get the same answer, or close to the same answer. If I didn't round it, have 91.44 and 91. I'm not going to count you too wrong on the answer. I would prefer that you rounded correctly. But what I'm really looking for when I grade your work is that you get all of this out and you recognize that the units cancel. So feet is here, and we had feet on bottom, so it cancels. Yards on top, yards on bottom, meters on top, meters on bottom. Centimeters is here, so that's what we're left with. Next, we'll do miles to kilometers, or vice versa, kilometers to miles. 15 kilometers equals how many miles? One big trick you'll see, if you see the giga, mega, kilo, centi, milli, micro, nano, any of those, the only thing you can do with that is convert it to the base. So I'm going to go ahead and put kilometers down here. The base unit for kilometers would be meters. So find over here, 1 kilo is 1,000 bases. So 1 kilometer is 1,000 meters. 1 kilometer is 1,000 meters. And then I can do something with meters to get to miles maybe. My length conversions are inches to centimeters or yards to meters. You could do it either way. It doesn't matter. The more you practice with this, the more you'll realize some are a little bit less steps than others, depending on where you're going. I'm just going to pick the meters to yards one. So 0.91 meters is 1 yard. I put meters down here, so it cancels out with the 1 up there. I know that for every 1 yard, there's 3 feet. And I know that there's 5,280 feet for every 1 mile. So I will take all of the tops divided by each of the bottoms. The easiest way to punch this in your calculator is to do 15 times 1,000 times 3 equals, divided by 0.91 equals, and divided by 5,280 equals. And I get 9.36563436. Remember what we said earlier about how we cannot report a measurement that's more precise than our least precise measurement? So over here I had 2 sig figs. I'm going to cut that off after 2 digits. Cut it off there. That 6 rounds up. I'm going to get 9.4 miles. Okay, next up, more unit conversions, just a little more practice. I'll do this one 2 ways to show you it doesn't matter which way we do it. We'll start with 3.4 liters. Trying to get to fluid ounces. I've got 3 options for my volumes. I can go liters to gallons. I could do milliliters to fluid ounces. I probably don't want to go all the way to tablespoons because that's a little bit different than I need to do. So let's do the milliliters to fluid ounces first. That happens to be the easier one for this one. I know I want liters on bottom. I can't do anything with milliliters and fluid ounces yet, but I do know that I can go from liters to milliliters because those are both metric. So liters are base, so base to milli, right there, 1,000 milliliters in 1 liter. 1,000 milliliters in 1 liter. Then, according to this conversion, I've got 29.57 milliliters in 1 fluid ounce. Punch that in your calculator, 3.4 times 1,000 equals, divided by 29.57, equals 114.9814001 fluid ounce. That's too precise of a number. I had 2 Sig Figs. So we're going to cut it off. 2 Sig Figs, cut it off at the tens place there. So this becomes 110 fluid ounces. Remember, that means it's somewhere between 100 and 120. Anywhere between there is fair game. If I had chosen to do liters to gallons first, we could totally do that, totally acceptable. There are 3.79 liters in 1 gallon. Says that right down here, 3.79 liters in 1 gallon. And then I can use all of these volume things here, just about all of them, to get all the way to fluid ounces. I know that in 1 gallon, there are 4 quarts. I know that in 1 quart, there are 2 pints. I know that in 1 pint, there are 2 cups. And I know that in 1 cup, there are 8, not 16, 8 fluid ounces. So I do 3.4 times 4 times 2 times 2 times 8 equals, divided by 3.79. And I get 114.828496. Again, too precise. I still have 2 Sig Figs, so we'll do 1, 2, cut it off. It's still 110 fluid ounces. It's still somewhere between 100 and 200 fluid ounces. Last one, we'll just do this one once. 3 miles to meters. So 3 miles. We're going to start with that. We know we want miles on bottom. The only conversion I have on this whole chart with miles in it is miles to feet. So we might as well just throw that one on there. 1 mile is 5280 feet. Now, here's where you're going to make a choice. For my length from US to SI, I could find a way to get all the way to inches and then convert to centimeters and then convert that to meters. So I could do inches to centimeters, or I could do yards to meters. Since I see meters in this one and I'm shooting for that one, I'm going to go ahead and go for yards for meters. I don't have yards yet, though, so I'm going to have to get feet to yards somehow. Those are both US units, so I look under US conversions. 3 feet is 1 yard. So 3 feet in 1 yard. And then for every 1 yard, there's 0.91 meters. And this gets you 3 times 5280. Oop, yeah, that's right. Divided by 3 times 0.91. And you get 4,804.8. We only had 1 Sig Fig, so we're going to cut it off here. That would round to 5,000 meters. If this had said 3.0, let's call it 3.0, that's fine. 3.0 miles, that's 2 Sig Figs. We would have rounded it off after 1, 2. We round it off there and we call it 4,800 miles. It all depends on that beginning measurement where we're going to end up rounding this and how many Sig Figs it had. Okay, let's see. If Jabba the Hutt weighs 500 kilograms, how much does he weigh in pounds? Easy peasy. What did I say earlier? If you see kilo or giga, mega, centi, milli, micro, nano, the only thing you can do is convert that to the base unit. So 500 kilograms, I want kilograms on bottom. The base unit for kilograms is grams. According to my chart, there's 1,000 bases in 1 kilo. So 1,000 grams in 1 kilogram. I want to know how many pounds. So let's look at our US to SI conversions for mass. I could do all the way to ounces and grams, or I could do pounds to 454 to grams. I'm going to do this one both ways to show you again that it doesn't matter which one you pick, you'll still get close to the right answer. All I want to do, or all I need from you, is to show that you can cancel units and do this method of conversion. So let's do the easiest one first. 454 grams is 1 pound, and that makes it super duper easy because we're already where we need to be. So 500 times 1,000 divided by 454 is 1,101.321586 pounds. I had one sig fig here. Let's pretend that there was a decimal. I forgot to type the decimal in, and that was actually 3 sig figs. So we'll go 1, 2, 3 over, cut it off there. This would become 1,100 pounds. Except I want these 3 to be significant. And we can't show that as a whole number like that. So we're going to write it as 1.1 times 10 to the, just kidding. We're going to write it as, 1.10, so that I can show there's 1, 2, 3 sig figs, times 10 to the 1, 2, 3 pounds. And that tells me that I've got 3 sig figs. I need that, and that's my answer. So basically 1,100 pounds, but I'm able to guess that it's somewhere between 1090 and 1110. If I had done it the slightly longer way, 500 kilograms times 1 kilogram is 1,000 grams, times, according to this, 28.35 grams is 1 ounce. That's different than a fluid ounce because up here it tells us there's 16 ounces in 1 pound. Just one extra step, but it should still get us to the same answer. So 500 times 1,000 divided by 28.35 and divided by 16 gets us 1,102.292769. Again, we had 3 sig figs, 1, 2, 3, cut it off there. It's still 1,100 pounds. Or, since I want to show 3 sig figs, 1.10 times 10 to the 3 pounds. Okay, here's the fun stuff. Are you ready? To report accuracy and precision, remember, accuracy is reported using percent error. That tells us, basically, how far away was my measurement from the actual or the theoretical or what it should be measurement. That's a Y there. Forgive me. Precision is measured by standard deviation. That's what the S stands for, standard deviation. So, let's see. I have a scientist who found a random chunk of metal in her lab somewhere. She wanted to know what it was. So she thought, kind of looks like gold. So I'm going to say that it's probably gold, and that is my right answer. That's the theoretical answer. And so this right here, I'm going to label it for you, is the theoretical value. That's what she should get when she does this test. So she thinks it's gold, and the density of gold is 19.3 grams per milliliter. She takes her piece of metal and cuts it up into 3 different pieces so that she can get multiple trials, because the more trials you do, the more likely your results are correct. And she determined the mass and volume to determine their density. And these were the values that she got. So if we want to know her percent error, we have to find her actual value. That actual means what she actually got when she did the experiment. This is the information she got from the lab. Theoretical is the what it should be, so 19.3. The actual, in this case, we're going to do the average, or as you might know it, the mean. So we'll do the average over here. Average, or mean, we find by adding them all up. 19.0 plus 20.2 plus 19.5 and dividing by the total number of data points. So 19.0 plus 20.2 plus 19.5 equals 58.7. Divide that by 3. You get the average is equal to 19.56666, blah, blah, blah. We'll just call it 19.6 grams per milliliter. This is our actual. We will use that for actual. Okay. This one is the easiest one. We're just going to plug it in. So we take our actual, 19.6, minus the theoretical, which was 19.3, divide by the theoretical, which was 19.3, and times 100. So that means our percent error is 19.6 minus 19.3 divided by 19.3 times 100 gets me 1.5544. We'll just call it 1.6%. So I'm saying my results are 1.6% away from the true value. Okay. That's how we show the accuracy, not accuracy. Who did that? Some dummy writing on this board without me knowing, I guess. Accuracy. Okay. Sorry about that. Anyway, next, to show the standard deviation, we do this equation. And it looks really hairy and really gross, but I promise it's not. So here's what we're going to do. The x1, x2, and x3 are the same as trial 1, trial 2, and trial 3. So those are going to go in place for x1, x2, x3. The x bar is the average. So this also happens to be x bar. So x1, x2, x3, that's all of this data right here. And x bar for each of these is this right here, the 19.6. N is the number of measurements we had, and we already found that. That's just 3. So if we plug this in, we get S equals, So if we plug this in, we get S equals the square root So if we plug this in, we get S equals the square root of x1, which was 19, minus the average, 19.6, squared, plus trial 2, 20.2, minus 19.6, the average, squared, plus trial 3, 19.5, minus 19.6, the average, squared. All divided by 3, the number of experiments we did, minus 1. I don't know why the minus 1's there, but it's just part of the calculation. Standard deviation, if you'll remember from the notes, tells us how close our measurements are together. That's what precision is. Accuracy is how right we are. That's why we compare it to the right answer, the theoretical answer. Precision, we're just comparing to each other to figure out how close our measurements are together. So for the precision of this, or for standard deviation, the closer this answer is to 0, the closer these answers are together. Because when we subtract them, that should be a much smaller number. And when we square it, that's an even a smaller number. And the smaller number this is, by the time you're done, is a smaller standard deviation. So if I plug this into the calculator, the best way to do it is not all as one thing, but do the parentheses and squared parts separately. So 19.0 minus 19.6 squared is 0.36. And 20.2 minus 19.6 is 0.6. Square is 0.36 again. And 19.5 minus 19.6 is negative 0.1. Square it, and you get 0.01. All over 3 minus 1, which was 2. So if we do that, we should get, let's see, 0.36 plus 0.36 plus 0.01 equals 0.73. Divided by 2 is 0.365. And then square root that. So the square root of 0.365 equals 0.604152299, blah, 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 blah. And we're just going to say, let's see, that was probably 1 decimal place here. We did all that. Let's just call it here to the 1 decimal place. That should be fine. So the 0.6 is our standard deviation. What do we do with that number? Great question. All we do to report this answer is write the average plus or minus the standard deviation. So I'm going to report this answer as 19.6 grams per milliliter plus or minus 0.6. So when the scientist reports her answer, she's saying, I measured the density of this piece of whatever it happens to be, maybe it's gold, maybe it's not, with a 1.6% accuracy, or 1.6% error, rather. I was 1.6 away from the actual answer, or from the theoretical answer. And I got 19.6, and based on the precision of my answers, they were close enough together that I could say they were within 0.6 up or down, plus or minus, from this number. So maybe I was 19, maybe it's 20.2, not exactly sure, but all of my answers should fall within that range. If it helps with percent error, if you want to trade out the word actual for experimental, so it makes a little bit more sense, sometimes that's an easier way to remember. I always just think of actual as being what I actually get in the lab. Theoretical is what theoretically it should be. But it might make more sense if you do experimental minus theoretical. Okay, that was a lot of work. I know it. Let's do one more example of this stuff, and I'm not going to write all of the extra stuff in. I'm just going to write the numbers in and show you what's going on. In this case, same exact sample of metal. We had 3 different scientists come in with their different instruments and try different ways to figure out the density. And these were the answers they got. And we want to know, were they accurate in their answer and were they precise? So first step, find the average. And we get, let's see, 17.5 plus 18.3 plus 25.8, all divided by 3. We get 20.5 grams per milliliter. Now that's quite a bit of ways from 19.3, so I'm guessing they're not accurate, but let's do the percent error anyway. These absolute value bars just tell you to ignore any negatives. So if maybe the theoretical value was bigger than this number, we'd have a negative up top. We don't care if the percent error is negative or not. We're just always going to report it as positive. So we'll do 20.5, the actual, what we actually got, minus 19.3, divided by 19.3, times 100. And this tells us that we have a 6.2% error, which is significantly bigger than our 1.6. It's 6 times more errorful, almost. So I would say, maybe not super accurate. For the standard deviation, this one should be obvious to you. It's going to be a much bigger number because these numbers are not very precise. They're pretty far away from each other, right? So our standard deviation should be a lot bigger than the 0.6 that we got on the last one. But let's find out. Standard deviation, so square root, trial 1, 17.5, minus my average, 20.5, squared, plus trial 2, 18.3, minus the average, 20.5, squared, plus the trial 3, 25.8, minus the average, 20.5, squared. Now I never seem to make this square root bar just quite long enough, do I? All right, so let's see, 3 measurements minus the 1. Figure out what all these are, 17.5 minus 20.5, that's probably negative 3. We could do that in our head. Squared is 9. Plus 18.3 minus 20.5 squared is 4.84. Plus 25.8 plus 20.5 squared is, that's not right, 25.8 minus 20.5 squared, there we go, 28.09. That's a really big one. But that makes sense because that's really far away from these other 2 measurements. Divided by 3 minus 1, which is 2. So we do 9 plus 4.84 plus 28.09 equals, divided by 2 is like 20.965. Square root that answer. And we get a standard deviation of 4.5, we'll call it 4.6. So that's a lot bigger than our 0.6 before. Now we're going to report this answer as being 20.5 grams per milliliter plus or minus 4.6. So now I'm saying this is anywhere between 15.9 and 25.1, which is pretty close. This one's 25.8. It's a little bit of an outlier here. But I've got quite a big range, pretty imprecise. I would definitely say it's not precise. If you have a standard deviation that is bigger than 1, it's definitely not precise. Your standard deviation should probably be a decimal most of the time, and the closer you get that to 0, the much more precise it is. And precision is important because we want to get the same answer every time. It's important to be right, but it's also important to be consistent. All right, those were all the examples that we did in class together. Good luck on your practice assignment. If you have any questions, please ask.